The third is the condition variables. So we need to check the condition before the execution for each thread. And parent node, sometimes they need to check if the child thread is completed, or they can check the state if there's any action need to make for different child thread states. So that's why we need a couple of calls to check the condition. And also we need to know when to complete the child thread execution. So if we don't do that, it will waste a lot of CPU resource, keep the parent thread running. And this is the logic structure for the condition variables. This is the main function. After we create this thread, the child thread, and then this part defines how to wait for the child. And in the child thread, we need to indicate the condition variables. And if we need to change it, we change it here. So a condition variable is a synchronization primitive to enable thread to wait for certain conditions to be met before proceeding. If the condition meets, then we can wake one or more of those waiting threads and then allow them to continue by sending a signal. So to declare this condition variable, we can use this. We can use this type pthread condition T and C. That means we declare the C as a condition variable. And there are two methods or two functions for the condition variable. First one is wait, and it can wait on a condition. And signal, which means it will be executed when the thread has changed something in the program, and then it wants to wake a sleeping thread, which has been waiting on this condition. So this is the wait and this is the signal. This is a code example shows how to use the condition variable, like some operations. First, there's a main function. The parent create the child thread, but it continues running. After the create the thread, it continues running the join to wait for the child to complete. And then the join here is simple here. It's just wait for the down value. If it's 0, it will continue wait. If it's not 0, it will move on, which means it will finish. And in this code, the child thread is defined. It simply just print the string child, then exit. And for the exit part, it will be change the down value to 1. That means for here, for the parent thread, it keeps checking the down. Then if it finds the down is 1, it will move forward to finish the this function. So the last part for the API, thread API, is locks. Locks used to lock a critical section, which means the data area or some data, and to be used for allowed thread only. So first initialize the lock, then start the lock, and then do some operations on the protected section or the data, for example, the X here. And then after the operation finished, we unlock. So when we try to lock some area, some protected section, what if other thread is holding the lock? What can this thread do? So in that case, the current thread has to wait. That means lock is one of solutions to the risk conditions. We introduced the risk condition problem in the first lecture. So we can use this lock to protect the critical section and then make some change to prevent the risk condition issues. So there are more locking mechanisms. Lock and unlock are not the only two functions for the thread. We also have some other functions like try lock, which means it will return failure if the lock is already held. So no waiting. It will check the lock status, and if it's already locked, then it will return failure. And timed lock, it acquires a lock within a timeout, which means it will wait a while. But if the timed locks timeout is 0, that means it's a try lock. It's going to be same. So the difference is about the timeout. Here list 2 shows the difference of these two functions. So if we have some locks, then how do we evaluate them? That means the goals to say the lock is good or bad, or is better than the other one or worse than the other one. So the first one is mutual exclusion. That means are the variable updates mutually exclusive? And the fairness, which means do all the contending threads get fair chance? Because there are sometimes we have many threads want to do operation on the same critical section. Then how to make sure one thread don't control the area for a long time to prevent other threads waiting for a long time. And performance with the overheads added while waiting for a lock. So how can we improve the performance? And if we have multiple CPU, then how do we design the locks? That's some basic questions or ideas we need to think about before we design the locks, or if we want to evaluate locks. So lock is good. It's good for the to solve the data race conditions, and it can protect the thread. But what if an interrupt signal happens? And if a program called, that means we need to do something, design some mechanism for this situation. So say if there's a interrupt signal here. So when we do the lock function, the first step, we can disable the interrupts, which means nothing can interrupt the current thread use the locked area. So by doing so, before entering the critical section, we can ensure the code would not be interrupted. That means I'm the only one, or I'm the only threads can use this area. No others can interrupt me. And after it's finished the operation, you can do the unlock. But in the unlock function, it will enable the interrupts first. Then that means I'm done using this area, so other threads can use this part. That's how it works. And there are some issues for the controlling interrupts. First, this approach requires us to allow any calling thread to perform privileged operation. For example, the enable disable the interrupts. Then we need to trust this facility is not abused, which means if a program is very greedy, could call the lock at the beginning of the execution and then monopolize the processor. That would be very greedy, right? Some applications they can do this, and for the worst situation, what if the program is a malicious program? It will call lock and go into an endless loop, which means like an infinite loop. like the while true function, it will run forever. So disabling interrupts is a general purpose synchronization solution, but it requires too much trust for the applications. If multiple threads are running on different CPUs and all try to enter the same critical section, it doesn't matter whether the interrupts are disabled. So threads will be able to run on other processors. So how do we design the mechanism to prevent this situation, or we just leave it there? That's also an issue. And interrupts are used limitedly. For example, in some cases, operating system can use the interrupt masking to guarantee atomicity when accessing its own data structure. That means need to prevent the operating system from being blocked by other threads. And this operation makes sense to the operating system because the trust issue disappears inside the operating system, which always we always need to trust the operating system itself to perform the privileged operations.